Yeah, good evening. Good evening, everyone. So, welcome to the fourth tutorial of the nuclear astrophysics course. So, last day we studied about the nuclear cross section of nuclear reaction, rate of nuclear reaction. All those we have done in the last class. So, now we are now in the nuclear physics, in the core nuclear physics regime of our course. So, I will today the class will be a more little mathematical because I have gone through the assignments and I thought that it will be good to give the mathematical overview before starting of the assignment so that you can understand those questions easier. So, first I will do some mathematical I mean formulations of what sir has already done. I will just give a recap of those to solve those questions. Okay, so uh, just few things we should remember from the last class that I will not again. Oh, it is. Yeah, mine is fine. Okay, so in the last class we have done that reaction rate of a equation of a chemical reaction, like 1 and 2 is making 3 and 4. So, in that case we can write the reaction rate as like this. So, 1 plus delta 1 2, where n1 is the number density of the first species or first element, n2 is the number density of the second element, sigma v is sigma correspond to the nuclear cross section, and v is the velocity of its target. Okay, so and the delta factor comes due to the symmetry. I mean, if 1 and 2 are same, then your delta 1 2 is 1. That's why. So, for pp, like p plus p reaction, where both the element which are going through the nuclear reaction is same, then the delta factor comes into the picture. So, all this we have done. This is the reaction rate. So, this is just a short recap, and we have also done the mean lifetime of a nuclear reaction, that can be written as nh sigma, not nh, so n of the species, which is for which species we are calculating the mean lifetime, that is the n, then the number density of that particular species is ni, and sigma v is same as the sigma v. So, this sigma v, you can see this term in everywhere when you are dealing with the nuclear reaction, and this particular term is very much important, as you have already seen. And also this mean lifetime can be written as rho xi divided by, I mean, n2 na sigma v. So, and there will be an inverse. So, all this we have done in the last class. We have solved some assignment problems also based on these particular equations. Okay, now so today we will go into some deeper knowledge of the nuclear reactions, and I will mainly in this tutorial, I will mainly focus on the resonant reaction, which has been the most important topic of the fourth week of this course. So, I will mainly focus on that particular topic, and all the assignment questions are mainly based on the non-resonant reaction. Sorry if I have said resonant reaction, not. We will focus on the non-resonant reaction, where you have already known the S factor. So, the S factor is very much important for this week's course. We will go through it, that S factor, astrophysical S factor. And for the non-resonant reaction, the S factor is behaves like a smooth function. You already know that. So, we will mainly focus on the non-resonant reaction. Okay, so let us start today's topic. Okay. So, before going to the direct questions, I told you that I will tell the theoretical background, which will help you to solve the questions. Now, okay, so what we have already seen in our previous week's course, that sigma v that I was every time writing, it can be expressed as 8 by pi mu kt 3 by 2 0 to e sigma e to the power minus e by kt d. So the sigma v was like this. Now it was the familiar expression to you. Now what we will do that at the beginning of the of this course, of today's lecture, we will just go through old topic. What I have done what I have done already, and I have shown to you in the previous lectures also, that when a reaction happens, that P plus P, suppose the hydrogen burning is going hydrogen burning is happening in the core of a star, and it is creating some helium. Okay, I am not writing proton number and mass number, everything, just proton plus proton by some reaction is giving you helium. Now you can calculate the Coulomb barrier of this particular reaction. Okay, this I have done in the first class and also in the second class assignment problem. So Coulomb barrier you can calculate for this particular reaction, which will be Z1 Z2 is square by R, where R is the separation between two proton nuclei and Z1 Z2 is the proton number of this species, which is 1 for this thing. Proton plus proton equals to helium, means two hydrogens are fusing and helium is generating. Okay, so if you calculate it with the R value of 1.44 into 10 to the power minus 13 semi, so you can see 10 to the power minus 13 semi means of the order of nuclear radius. So if two protons are coming closer and if their distance is this much, 1.44 times 10 to the power minus 13 centimeter, then that will go through the fusion and it will create helium. So if you calculate the potential at this particular distance, just replacing the R here, you can see the potential will be 550 keV. Okay, so the reaction, it is the required energy to have threshold energy, whatever you can say, to occur this equation is actually you should have a temperature of that core where the nuclear burning, proton burning is happening, should be of the order of such that kT, which is the thermal energy, should be order of 550 keV. If your thermal energy is equivalent to the potential barrier, Coulomb barrier of proton-proton nuclei, then your proton can overcome that distance and it can fuse with the another proton and the helium will. Yes, anyone someone has any question, you can ask. Okay, if you have any question you can ask. So okay, so the I was just what I was telling, that if your temperature is such that your kT, which is the thermal energy, is 550 keV, then that reaction can happen. Now for this calculation you can find that if your T is of the order of 6.4 into 10 to the power 9 Kelvin, then your kT is 550 keV, and that reaction can happen if the temperature is 6.4 times 10 to the power 9 Kelvin. Now in suppose our star, so the core temperature of our sun is about 15 million degree centigrade, 15 million Kelvin. Okay, that means the temperature is 15 into 10 to the power 6 Kelvin, or roughly you can write 1.5 into 10 to the power 7 Kelvin. Okay, so this is the temperature of our sun's core, and this is the temperature which is needed for the proton-proton reaction. So it is obvious that at this temperature, which is very very less than the required temperature of 6.4 times 10 to the power 9, so you can see here it is 10 to the power 9, here it is 10 to the power 7. That means 2 order of magnitude lower than the required energy. But we know that in the core of the sun, proton-proton reaction is happening. So that is the puzzle. You can say that how the reaction is happening in a very low temperature than the required temperature. So what is the main procedure by which this reaction is happening? And it cannot happen classically, because here I have shown that all the calculation till now I have done is classical. In the classical limit, you should have this much temperature to go to get the proton-proton reaction. Okay, so the obvious question is how this reaction is happening at a very low temperature of 10 to the power 7 Kelvin. Low I am telling comparable to the required energy of 10 to the power 9 Kelvin. Okay, that's why I am telling low, although this temperature is not low. Now here comes the quantum tunneling effect. So the quantum tunneling, I don't know whether you know it or not, because it is a, I mean it is a, I mean it will be taught in second or third year of your BSc. So quantum tunneling effect I will tell briefly. Now what I will do that. Okay, another thing can happen before going to the quantum regime. People have tried to explain it through the classical limit. It's like, okay, I have a so I have a Maxwell-Boltzmann distribution at temperature T equals to 1.5 into 10 to the power 7 K. So suppose this is the Maxwell-Boltzmann distribution of T at 1.5 10 to the power 7 K. Now, so this is the peak of the distribution. So most of the particles have a kinetic energy correspond to that kT, where T is the, this T is exactly same as this T. So kT is the energy of this particle, most of the particles. But there are few number of particles, like this number of particles or this number of particles in the higher energy limit. Okay, so if it is E, E1, E2, E3, E4, then your E4 is greater than E3, greater than E2, greater than E1, greater than E. Okay, so although your maximum number of particles, and this E, where the maximum number of particles is there, that is this kT. Okay, so E is kT, where T is 1.5 10 to the power 7. So at this particular temperature, maximum number of particles are there, that is fine, no problem. But few number of particles, which is denoted by this 2 area, that is in the region of E1 to E2 or E3 to E4. So few number of particles will be there in the high energy limit, which have energy. So if you calculate kT, which is corresponding to the energy of E1, say, where E1 is much greater than E, then there you will get some particles with the higher kinetic energy, higher thermal energy. So I want to say that this small number of particles can be responsible for the proton-proton reaction, although the peak of the distribution is at a very low temperature. But it can be calculated. Suppose what sir has done, I will do the same thing. Suppose your T is 0.01 into 10 to the power 9 Kelvin or 10 to the power 7 Kelvin, comparable to this. Okay, this is 1.5 times 10 to the power 7 Kelvin into sun, and here it is 10 to the power 7 Kelvin, and corresponding energy is 0.86 keV. So if you try to find out the number of particles at this particular temperature, this problem I have done it in the last last session also. So if you try to calculate the number of particles, you will get it 10 to the power minus 275. Okay, so that means at a lower temperature you have a very small number of particles. So classically this can you see it, this is 10 to the power minus 275, a very small number. This small number of particles cannot be responsible for the rate of proton-proton reaction, which we infer from the observation at the core of the sun. So classically it is possible with a very faint chance, but it cannot be accommodated with the reaction rate. So the quantum picture comes into the survival, and the quantum tunneling effect has been assumed. So now we will move to the quantum tunneling from the classical limit. Okay, so what happens generally? Okay, I will okay, no problem, I have a page. Okay, now very briefly I will tell you how the quantum tunneling effect. Okay, yeah. Now suppose this is your potential barrier, which is the which will look like this, that it is the value of Vc. So it is the potential I mean the value of Vc is this much, and it is the R. So suppose two protons are coming closer and closer, and if they have like this, so if they have energy like this, they cannot overcome this wall classically and cannot go into this region, where the nuclear reaction will happen, because it is inside of the nuclei. Okay, so but quantum mechanically, if the particle has energy of this much E, there is some probability that the particle will overcome the potential barrier, and it can come to this region where the nuclear reaction is happening. This is actually the quantum tunneling. Why it is tunneling? Because it is like it is creating some tunnel here inside the potential wall, and it is going to the other direction of the potential wall, which is not possible for the classical particle, because for classical particle the particle will come and it will reflect back from the maximum potential wall, but quantum mechanically it will come to this region, which is called the quantum tunneling. So quantum tunneling we will study briefly for this thing. Now the famous Schrodinger equation tells you h square by h cut square by 2m gra square psi is equals to, this is the famous Schrodinger equation. I cannot derive it. If you know it, very good, otherwise if you can remember it, that is also fine. So here psi is actually the wave function associated with every particle. Okay, now if I write this equation in 3 dimension, then it will, and we will take the radial part. So 3 dimension means we are going to the r, theta and phi coordinate, and we are writing our equation in the r coordinate only, because if you write this equation, this gas square, in the 3 coordinate, you will get del r square, del theta square, del phi square, and from that equation you can equate 3 different equation for r, theta and phi separately. Okay, so we will only consider the radial part. So if we write the radial part of the equation, it will look like this. So del 2 del r square r psi is equals to Vr minus E psi. Okay, so this is the equation which we need to solve here. That m can be written as mu also, because we are considering 2 particles, and mu will be the reduced mass of the 2 protons. So mu equals to m1 m2 by m1 plus m2. Okay. Yeah. Now, so now what is Vr? When to if anyone has questions, just unmute yourself and ask the question. Yes, just spherical coordinates r, theta and phi. Yeah, and I have written the equation for the radial part only, because that is the most important part. Theta and phi direction, we are assuming there is symmetry for the simplicity. Okay. Cartesian coordinate you can also use, no problem in that. In that case, you have to formulate your equation in such a way that is useful to your problem. So generally we use Schrodinger equation according to our problem. If we are dealing with a simple harmonic problem, I don't know you have done it or not. So if you are doing 1 dimension simple harmonic oscillator problem, in that case you will find that we only deals with the 1D Cartesian coordinate, because the problem says it is much simpler to use. Okay. So Schrodinger equation we solve according to our problem. Okay. So this is the radial part of the equation. Now one few assumption we will do, otherwise we cannot solve this equation, because this Vr you can see for the real problems, for almost 90% of the real problems, this Vr is quite not so simple. So we cannot solve it analytically, and we have to use the numerical method to solve the equation. But for some case, some idealistic scenario, like I told you, the simple harmonic oscillator, we assume a simple version, a simple expression of Vr, so that we can do it analytically by hand. So that same thing we will do here, and as I told you in the beginning, that Vr is actually Z1 Z2 E square by R. When 2 protons are coming towards each other, R is the distance between the 2 protons, and Z1 Z2 are the charge. Okay. So and assumption is that the radius of closest approach, that means the radius, the nearest not nearest, the smallest distance between proton and proton, that is actually your radius of closest approach, which is which I will write at r1. So r1 is a particular value, not a variable. So v of r1 is actually E. That means if it is your radius of closest approach, then your energy should be equals to that potential at that particular distance. Okay, so it is, if it is r1, I am just saying, then at the position of r1 your v is equals to E. Okay, so that is the condition of the closest approach, and if you calculate it, it will be z1 z2 square by r1. I have just replaced r by r1. Okay, now if I want to write VR, our VR was z1 z2 square by r. Suppose I am writing it like this way, z1 z2 square by r1 into r1 by r. So that is same. Now don't consider this figure, I will come into it later. So I have just write that I have just divided with r1 and multiplied with another r1. Now z, this first term is actually this E, right, which is the energy of the particle. So VR can be written as E r1 by r. Okay, this you can write just by some algebraic manipulation. So V is E r1 by r, where E is the energy at the closest approach. Now this is the VR. So in a nucleus, so if it is proton, if it is hydrogen, there is only proton. But if it is not hydrogen, it is some helium or some higher order elements, so the nucleus is a spherical like structure, and it is not only a single proton, there will be a collection of protons, collection of neutrons, and it will be a solid ball type thing. Okay, so that's why what we do, we generally calculate a mean volume average of the potential height. Okay, so from VR we generally calculate the VR. I am giving this bracket, this curly bracket, which means the mean volume average potential. So this potential I will average it over the nucleus volume. Now if the nuclear radius is 4 pi r square, this can be done by this. If you don't understand every step, no problem, I am just trying to give you the idea. So 0 to r1. So this will give you the volume averaged potential. Now if you calculate it, it will come out as 3 by 2 E. So all this was some assumption, some simplification of the problem, so that we can solve the Schrodinger equation by hand. So our volume averaged potential is 3 by 2 E. Now we will just put this 3 by 2 E in the place of VR in the Schrodinger equation, what we have already written. So here minus h square by 2m 1 by r. So here I am only writing the radial part, so you can use the d2 also, because all the other coordinates are not here. So 3 by 2 E, just I have replaced, minus E psi, that will give you E by 2 psi, the right hand side. Okay, so now you have to solve this equation. Now I will not do solve the equation, I will just try to give you the thing. So just remember. So you will find this type of equation in hydrogen atom problem also, same type of formula. So this is the equation which tells you the is the Schrodinger equation of the particular problem which we are dealing with. That problem is two protons are coming towards each other, or you can say one proton is stationary and one proton is coming, no problem in that, and the reaction will happen. That is our problem of, and we have expressed the Schrodinger equation of the particular problem. Now from here we generally, what is the procedure, we need to calculate the psi, and if you have the psi, so psi will be a function of r, that psi r square will give you the probability of the particle which can be found at a particular distance. So psi r square, r equals to suppose capital R. So I am trying to find out the probability of the particle at a distance r, which can be calculated by this. Okay, so that exactly same thing I will do. This was the part which has not covered in the class, but from there what I will say, it is covered in the sir's class also, you can understand that. So remember here I have told you that R1 is the radius of closest approach. So it is classically, because I have taken this particular point and I have told you that it is classical regime. I have not come to this region yet. Whenever I am coming to this region, I am going to the quantum domain. Okay. So if you calculate the probability psi of R 0 mod square by psi of R1 square, and as we are dealing with the spherical geometry here, extended body, so you have to multiply R0 square and R1 square here. So I will what R0 square and R1 square, it is the same thing what sir have used at RC and RN, where RC was the classical radius, RN was the nuclear radius for his lecture, and for my lecture I have used the RC as R1 and Rn as R0. So it is the classical radius and it is the nuclear radius, what that is coming from the quantum thing. Okay. So if you want to find the probability of particle at a nuclear radius, that will be given by psi of R0 whole square, and the classical probability of finding the particle at distance R1, which is the classical radius, that will be coming from the psi of R1 mod square. Sorry, it will be mod square, and this R0 square and R1 square is coming from the spherical geometry purely because it is a extended region, and this 4 R0 square is actually telling you 4 pi R0 square dr is actually the volume of the nuclei, and 4 pi R1 square dr is telling you the volume of the classical, I mean nuclei, I will say classical nuclei. So that's why this R0 square and R1 square are the volume element which is coming into this picture. Okay. So if you calculate now exactly same thing, so for your better understanding I will write psi of Rn square. So if you go through the sir's lecture again, so you will find sir has used this notation, psi of Rn square by psi of Rc square, where I have written is psi of R0 square by psi of R1 square, exactly same thing. Okay. Just two different way of introducing R1, I mean expressing. Now if you calculate it, it will be this I cannot do it because it will be very time taking, 2 beta R1. So just remember, whenever you are trying to find some probability of a 3D spherical geometry at a particular distance, so it will be like exponential 2 beta R0. R0 means at the distance you are wanting to calculate the probability, and R1 is at the distance you are calculating the probability. I mean R0 and R1 at the distance related to your problem, and this beta is actually okay. So this beta I will write later. So for our case, that our R0 is R1 is very greater than R0. Okay, that means, I mean for my nomenclature I have used that R1, so it is my 0 for the R distance and it is increasing towards the R. That means my R1, which is the classical radius, that is larger than the R0, because R0 is this one, this thing, the nuclear radii. Okay, so R1 is greater than R0. I am in that limit, and in that limit you can write it as, it is just an approximation of R1, just an approximation for simplicity. And so exactly similar way sir has written this at RC, I think. Okay, because RC was the classical radius. Now this is the thing. Now if you put the beta value, it will be like exponential minus 2 pi by h cut mu by 2e z1 z2 z1 z2 e square. This you will get from by solving the equation. That is exactly coming from the beta. So if you put the beta accordingly, you will get this solution. This solution is, you have to remember, and I will write it exponential minus b by e, which is equivalent to exponential minus 2 pi eta, which has been used by sir. So it would be exponential minus b by root t is exactly as same as exponential minus 2 pi n. Okay, so I think this is the a more simpler way to understand it, because in this type of expression you can explicitly see the dependence of energy which is coming by root over E, and all the other terms I have been written in the B. So the explicit understanding of energy is there in the particular expression, so I took this particular thing to continue. So exponential minus B by E, which we got, it is the gamma factor. Okay. Now if you calculate this, you will find that by putting the typical value of a nuclear radii and typical value of classical radii, the probability is roughly 10 to the power minus 10. Okay, 10 to the power minus 10. Remember this value, and for the classical limit it was 10 to the power minus 275. So 10 to the power minus 10 is although small, but it is much higher than 10 to the power minus 275. So considering the quantum thing, our probability of reaction is have been increased by several orders of magnitude. 265 order of magnitude we have been increased by it, and 10 to the power minus 10 is a good number for this reaction. So due to this analogy, we can say that quantum tunneling is the main effect, or the main reason, not effect, main reason of the proton-proton nuclei or any fusion reaction that will go through the quantum tunneling part. Okay, so this we have done, that our probability is exponential minus 2 pi n. Now we will do the gamma thing. Okay. Okay, so what we see that now this picture is important, because this number of particles curve, it is coming from the Maxwell-Boltzmann distribution, and as I showed you this this thing, this Maxwell-Boltzmann distribution curve, where when you are going to a higher energy limit, where is the x-axis energy, your number of particles is decreasing and the probability of fusion is increasing with energy. Okay, so there is a balance between these two, so this and this, and there will be a region, particular region, this region, where the probability of the reaction is, I mean, much larger than the probability of the all other energies. So this is the gamma factor, I mean gamma peak, and this is the reason why the all the fusion reaction will happen. So the fusion reaction mainly will happen in this particular region, when the gamma range, I will tell you the gamma range is there. Okay, so now what we will calculate, so it is very simple, that one thing is decreasing like this, one thing is increasing like this. Now if you want to sum these two curve, then there will be a part, there will be a portion where there will be an increase in the resultant curve. So that is the gamma peak actually, otherwise it will be decaying, or on the both side. Okay, because if it is like what I will tell you, like this is 5, the value of this point is 5, the value of this point is suppose 1. So 5 plus 1 is 6, and suppose it is 4 for both of the curve, so it is 8. So it is 6, here the value, resultant value is 6, here the resultant value is 8, and again here the resultant value will be low. So I am just trying to give you the idea. So the peak value will be around this portion where the two curve meets actually. So that is what coming from the gamma peak. Now so just remember this thing, that our probability is exponential minus b by root over e, because it will be needed. Now so sigma e, which is the cross section, is proportional to the probability, that is proportional to exponential minus b by e. Now what I will tell you, this will be useful directly for the calculation of the assignments problems. And also you know that sigma e, classically it can be written as pi lambda square. It has been shown in the second week or third week lecture. So and lambda is the de Broglie wavelength, that is h by 2 me. Okay, so lambda is proportional to 1 by root over e. If I put that here, it will be pi 1 by e. right? So your sigma is proportional to exponential minus b by root over e, and sigma e is also proportional to 1 by root over e. I am not writing that pi term. So the total sigma e will be proportional to exponential, it is a combination of two things, times 1 by e. Okay? And if we include, if we want to convert our proportional sign to the equal to sign, there should be some factor. So that is SE. S is the factor of that, I mean converting from proportional to the equals to. So exponential minus b by root e. So this is the most this is the most important thing. Sigma e is proportional to SE by e exponential minus b by root over e, where your SE is actually the astrophysical S factor. Astrophysical S factor, which is the utmost important part of our 4th week's material. Okay, so sigma is this. Now always remember one thing, I mean, as I am using a differential, that exponential minus b is exactly exponential minus 2 pi n, which has been used by Sir. So that's why I am writing it here again. The 2 pi n has, that nomenclature has been used by Sir, and I am using this one. Now, okay, so for what, and now at the beginning of the lecture I have written this expression, which is the sole purpose of doing all these mathematical terms, because the sigma v, whenever you are calculating the reaction rate, the mean life, whatever, this sigma v term is very important. You have seen everywhere that sigma v term, the mean sigma v, because it is in the curly bracket. So that we will write, it was 8 by pi mu, that expression I am just writing here, kt 3 by 2 0 infinity e sigma e to the power minus e by kt dE. Now we have a expression of sigma e here, and we will just put that sigma e in this particular expression. So I am not writing this particular term. Okay, this is there, 0 to infinity e s e by e exponential minus b by root over e, and that. Okay, so that means 0 to infinity e will be cancelled out, AC will be there, exponential minus b by root over e minus e by kt dE. Okay, so this is the, so that plot I showed you, so it is the same thing. So this plot is actually for exponential minus b by e. Okay, and this particular plot was for exponential minus e by kt. So you can see, if your e is going to if your e value is small, then this exponential minus beta b by e, this will go to a 0. So at small distance, small energy, that is going towards the value 0, and the exact opposite case is for the other curve, which is number of particles curve. So when the e is going to a higher value, that means e is in the numerator, and e is going to a higher value means higher negative value, that is the total expression exponential minus e by kt, that will go to a 0 value. So that you can see here, that for a higher value of e, the number of particles curve is going towards a 0 direction. So this is exactly the balance between the two, where the gamma peak lies. So this expression is very much important, don't forget this factor is there, and this will tell you many information about the nuclear reaction. Okay, now suppose it has been given in the question that what is the peak value of the gamma plot, what I have shown you. So what is the peak value? So that we can calculate. So for the peak value is 0. So peak value means at what energy the curve, this particular thing, this particular thing has a maximum or minimum. So the condition of maximum is minimum is the first derivative of that particular expression of 0. So if you want to find the maximum or minimum of Fe, at first you have to do del F del E is equals to 0, right? That will give you the value of E, and by doing the second derivative you can tell whether it is a maximum or minimum. So, we will do the same thing. The peak value E0 can be calculated by DDE of exponential minus B by E minus E by KT is equals to 0. So, from there here we will calculate, it will give you B is there, B 2 e to the power 3 by 2 plus 1 by KT equals to 0. That means your there will be a minus sign here, right? Yeah. So, this will give you E is equals to BKT by 2 to the power 2 by 3. Okay, so that will be the value of E. Now, one thing I have done here. So, here from this line to this line I have just written the root over E here, which was this term, and all the other thing I have been done I have been written in B. So, there will be an expression of B which you can write it from here, all the other terms. That means all this is actually your B, except that so that 2 is also in the B. Okay, this 2 is also in the B. Just so except this root over E in the denominator, every other terms I have been absorbed in the B. Now, if I write that if I express that B in the all the terms, so you can find it E equals to 2 pi by h cut mu by 2. Just do it yourself. Z1 Z2 e square KT by 2 by third. Okay, and for some typical values it has been written in a simpler form, Z1, so Z1 square Z2 square yes mu t to the power 6 to the 1/3. It is in keV. So, for we have just put the value of pi, h cut, Z1, Z2, k, everything those are constant. Just t is a variable, that's why here t is there, and Z1, Z2 is variable because for defined elements it will be defined. So, Z1, Z2 is here and the mu is here, that is also depend on the elements, and all our other constant we have put the values. And so, the E, so I should write it as E0 because it is the peak, right? 1.2 Z1 square Z2 square mu T6 1 by 3 in keV. Remember that it is in keV. So, T6 is T by 10 to the power 6. So, this is the important thing. This is one of the important result of the calculations which is needed for the equation. So, what suppose you have been given the two elements which are going through the reaction. So, you know Z1, you know Z2, you can calculate the mu from the mass. And one more thing, the temperature should be given in the question. So, if all those given, you can calculate what is the gamma value, I mean what is the value of E0, peak value of gamma plot. Okay. So, that type of problem we will do. So, that is why I thought it will be helpful if I do the calculation, because directly in the problem writing this expression will be difficult for you to understand. So, we have just what I have done, that sigma E I have from the quantum mechanical problem, the probability I have calculated as this, and sigma is proportional to probability, sigma is also proportional to 1 by energy. So, I have got the total, I mean expression of sigma E, which is this, and that sigma E I have just put the familiar equation of the sigma V mean, and we got this factor, which is very much important because one curve is going down at a lower energy, at higher energy, one curve is going up at higher energy. So, we have found a region in between them where the probability of the reaction is higher, and by maximizing that particular expression, we have calculated the exact value of E0 for which the peak of the gamma curve is there. So, yeah, this is the gamma peak and this value is E0, at which value that peak is there, that we have calculated. Okay, so, this E0, and as you can see it is a Gaussian type of profile. Okay, so, there will be a certain width also. So, that width we will also calculate. So, if there is any Gaussian plot, the main factors are the peak at the I mean where the peak is located and the width. So we will do the now we have calculated the peak value. Peak value means the value of energy for which the peak is there, and now we will calculate the width. Okay, so E0 is done. Remember this, I will use this repeatedly in our equations. Now yeah, so okay, now going to the same thing, sigma v we have written as 0 infinity this particular thing, okay, this thing, this is sigma v. Okay, so I am writing it as proportional because I will not write the first term here. If you want to write equals to, just put the first term here. So 0 to infinity exponential sorry, I have write the SE exponential minus b by root e minus e by kt. Okay, so this was, and there was dE as it is an integral. So this particular thing which is it can be written by it can be written by Gaussian form. So Sugandha Khangar, can you just turn off your video because it is, I mean changing the orientation, and if you can just turn off the video. Okay, so as I was telling that exponential minus b by root e minus e by kt, that is the term which is can be written as exponential minus okay, so first I will write the b to get a better understanding, 2e z2 e square minus e by kt. I have just put the value of b, and it can be written, that I will not do, I have done it, it is a very lengthy, I mean calculation. So it can be written as like this, E0 square by delta by 2 square. Okay, so it is the approximation, I should not give the equals to sign. So this is the approximation where your exponential minus 3E0, E0 is the value which I have already calculated, and 3E0 by exponential 3E0 by 2 is your I max. I max means the maximum value of the gamma plot. So this maximum value is we have denoted by the I max. Okay, so I max is the maximum value, and exponential minus E0 square by delta by 2 square. So delta by 2 is actually the half width. So I told you that this was the gamma, roughly my drawing is not good, so this was the gamma peak. Okay, so it was E0, this was delta. If this is delta, so that means this half part is delta by 2, this half part is delta by 2. So we have expressed the gamma peak with the Gaussian thing in this way. So your this range lies from E0 minus delta by 2 to E0 plus delta by 2. Okay, because if it is delta by 2, that means this ending is E0 minus delta by 2, and it is E0 plus delta by 2. So all the reaction will mainly occur in this particular region, that is if the energy is in the range of E0 minus delta by 2 to E0 plus delta by 2, then almost majority of the reaction occurs. So that is the importance of the width of any Gaussian curve, that tells you so what is the major region of that interaction. Okay, now this delta have been calculated. It is 4 by 3 E0 kt to the power 3 by 2. So if possible, try to remember this expression like this one. It will be very beneficial for your exam, because every time you cannot do it from the basic. So if you can remember it, it is not that much tough, because 1 by 2 factor you have to remember. Z1 square, Z2 square are just the proton number. There will be a reduced mass and the temperature to the power 1 by 3rd. Okay, so my 1 is not 1 by 3rd. Just try to remember. Also try to remember this particular thing if you can. If you can't, then the last line you have to remember, the last line what I will write here, because that will be useful for your solution question. So E0 was this thing. I will write that E0 here 1.2 Z1 square Z2 square mu T6 square. So there was T6. Oh, one thing I have missed out. There will be a T square T6 square. So just do it. Okay. Yeah, because it was T to the power 2 by third, and here I have written 1 by third outside. That means there will be a T square. Okay. So T6 square to the power 1 by 3 KT half. Oh, another thing, when you remember this, just remember this 1.2 factor with this T6, because you have expressed your T in terms of T6, that's why that 1 by 2 factor has come. If you have written it in terms of T, original T, not in T6, then that factor will be different from 1.2. So this 1.2 and T6 combination you have to remember. Okay. Here also we will write everything in T6, and we will express our result in terms of value which has been calculated if we use T6. Okay. So Z1 2/3, Z2 2/3, mu to the power 1/3, sorry 1/3, T6. So T6 2 by 3 here. Here is also a temperature to the power half. So 2 by 3 plus a temperature to the power 1. So 2 by 3 plus 1, that will be 5 by 3 and half. Okay. So this will be 0.749 Z1 square Z2 square mu T6 to the power 5 1 by 6 in keV. Okay. So if you cannot remember this part, just try to remember this expression at least. That will be helpful for the problems to solve. So we have calculated the E0 and the delta of the gamma peak by assuming it is a roughly Gaussian, it has a roughly Gaussian type profile. So because here from this step to this step, here it has been assumed that the structure is like Gaussian type, otherwise you cannot do it. So delta and E0 we have calculated. Fine. Now, yeah, yes. Okay, Gaussian, yeah, I should tell you, I have also written down. Okay, so just don't focus on the question right now, because I don't have much many pages. Okay, so if you have this type of profile, this is a bell shaped type profile, that is called the Gaussian profile. I mean, it can be expressed like this: fx is 1 by sigma 2 mu 2 pi exponential minus exponential x minus mu square by, okay, so I will write it like this, root 2 sigma minus. Okay, so this type of profile, so if you don't remember this also fine, just to understand, if you have any function that has this type of form x minus x0 square divided by some number, some constant or whatever, just say. So if you are dealing with this type of equation, exponential of minus x, okay, so exponential minus x square, if your x0 is 0, that means exponential minus x square. This is also a Gaussian. Now if you plot this particular thing as a function of x, fx, it will give this type of structure where the peak will be at x equals to 0. Okay, so this is called the Gaussian type function. Fx e to the power minus x minus a whole square, this type of profile is generally called the Gaussian type profile, and it has a this bell type shape, where and now if you plot this particular thing, it will be just slightly shifted, but will be a Gaussian, and the peak will be at x equals to a. Instead of 0, the peak will be at x equals to a. Okay, so this is called the Gaussian type structure. It is a very crude way to express. Now the main Gaussian function, if you Google it, you will find it like this. Here also you can see, here I have written minus x minus a whole square, here it is written as x minus mu whole square, with the term in the denominator. You can say here the denominator term is 1. So those are not so important, because this mu is actually the mean of the distribution, this sigma is the variance of the distribution. All the parameters are there, you don't have to understand all those right now. But whenever you are seeing like this type of distribution, this type of function, that is a Gaussian function. Okay. Yeah. Okay. Now, okay, so it was the Gaussian thing. So we calculated delta and E0. Now what we will do, it was the second thing. Just a second. 1, 2, 3. Yeah, now I can go to some of the problems which can be solved. So yeah, so in blue I will just write E0 again I am writing it because it is important. 1.22 z1 square z2 square mu t6 1 by 3 in keV unit, and your delta is 0.749 z1 square z2 square mu t6 to the power 5 1 by 6. Okay. In keV, it is also in keV unit. These two we will use repeatedly. Okay, now one thing is there, I will tell it while doing the problem, another thing. Okay, so let us go to some of the problems, like the first one, that at stellar temperature T6 equals to 15, means T6 by 10 to T by 10 to the power 6 is 15. That means your T is 15 times 10 to the power 6 Kelvin. This is the method of expression. So at stellar temperature T6, that is 15 million degrees Kelvin, the effective burning energy, so we have calculate the gamma peak for PP reaction. Okay, that means we have to calculate the E0 at where the gamma peak is, and as I told you, E0 is this one. I will just use this particular expression. So 1.22, Z1 is 1, Z2 is also 1, because we are dealing with the protons, mu T6 to the power 1 by 3 in keV. Now your mu, so one thing also you have to remember, that this 1.22, as I told you, that 1.22 has, one second, have I done anything wrong? Yeah, here I have written is 1.2, but precisely it is 1.22. Okay, no problem. Now this 1.22, as I told you, is a combination of 1.22 and T6 is necessary. You have to remember, because it has been expressed in such a way. Now another thing also you have to remember, that this mu, it has also been this expressed in terms of AMU unit. Okay, so you don't have to put the AMU unit by hand, because the factor has been already taken care of that AMU unit. So you can just calculate your mu is M1 M2 by M1 plus M2. So your for proton, your M1 is 1 AMU, right? So you just write 1. You don't have to put the AMU separately. So M1 M2 by M1 plus M2, that will be 1 by 2, that is 0.5. So if it is 2 oxygen, then you have to put the 16 by 16 plus 16. You don't have to put the value of AMU, because it has been taken care already in that 1.22 factor. So we will 1.22, that mu is 0.5, and T6 is given 15 into 10 to the power 6, 1.3 keV. Now if you calculate, so here I have also again missed that square term, right? Yeah, you also, none of you have told me. Yeah, mu equals to mu T6 square. So that square is there. So it will be a square, right? 1.5 times. Yeah. Now if you do this, and I have done one mistake. What I am telling you to not do, that I am doing myself. So it has been expressed in terms of T6. So no need to put 15 into 10 to the power 6. Only put 15, because it is already in T6 unit. Okay, so mu is 0.5 times 15 square just. The 10 to the power 6 is not required, it is already in this factor. Okay, now if you calculate, it will be 5.9 keV. So you can see the math, I mean the mathematics for this particular problem is very easy, but you have to understand that E0 and delta, and if you by any chance forget it, just try to remember it is coming from the exponential minus b by root over e minus e by kt. Just take the first derivative, make it 0. You can do the second derivative also, but the second derivative will give you the maximum. I am telling you that will not give you the minimum. You can check it also. So just take the dd of that particular expression and put it 0. If you forget by any chance, then you will come up with this particular E0. But this delta is quite difficult. It will be good if you can remember this delta term. E0 can be calculated very easily, but not delta is not that easy to calculate. Okay. So this 5.9 keV, this is the answer, and this type of problems are there in the assignment. So I told any of one student to send me your current 4th assignment, but none sent me. I could not go through that assignment as I don't have access. Now today again I am telling you, just if possible any of you send me your 4th and 5th current assignment, because this question which I am solving here, it is from the older assignments, as I told you earlier also, because but you can find these questions also in your new assignments, but just give me the 4th and 5th assignments of 2023, so that I can go through the problems, and if there is any problem which I have not done, I will also go through those. Okay, so just one of you please send me the 2 assignments in this email ID, if possible. It is sourav@iisc.ac.in. Okay. Now coming to the second problem, it is asking for, so there is a reaction. Sorry, yes, anyone wants to take? Okay, so this is also a proton. Sorry. Oh, you are writing the email ID. Okay. Just send me. Okay. There is no space. It is SOURAV continuous. Yeah. Okay. Thank you. Just send me that. Okay. So coming to the second question. So here it is also P plus P helium reaction, proton plus proton equals to helium, and your Q is given. Q value has been measured at the center of mass of energies of 10 keV, the Coulomb barrier of DP reaction. So we need to calculate the Coulomb barrier. Okay. So Coulomb barrier is actually coming from ECs, that was Z1 Z2 E square by R. So if a particle Z1 is here, Z2 is here, the electrostatic potential you can calculate, and that is actually the Coulomb barrier. And if the distance is r, so Z1 Z2 is square by r, which we have done. And for proton it is 1 into 1 and E square, just put it the value of E, and it will be keV semi unit, and the R is can be R0 is 1.2. Okay, so R0 is given. I don't know why the Q and ECM is given here. I don't find. Okay, so center of mass energies is has been told, but it can be done in this way also. No need to go through that particular thing. Okay, so R we have to write. Now, as I told you in the last class, that your R is actually can be written as R0 a to the power 3 by 2, where a is your mass number and R0 is given in in the value 1.2 angstrom. It should be 1.2 angstrom. Yeah, okay, right. 10 to the power minus 10. I don't know. Minus 10 meter, 10 to the power minus 12 semi. Yeah, 1.2 angstrom means 1.2 angstrom. That means 12 into 10 to the power minus 13 semi. So whenever you get this value, this type of value 10 to the power minus 13 semi, it is the range of nuclear distance. Okay, so it is femtometer, as I told you in the last class. So R can be written down as R0 a to the power 3 by 2. and as we have two separate thing, it will not be square, it will be r0 a1 1 by third, a2 1 by third. A1 and a2 are again 1 and 2 for our problem, because one is proton and another is helium. Okay, one is deuteron and another is proton. So deuteron and proton. So for deuteron, the there will be a proton plus neutron in the nucleus. Okay, so that's why it is 2. So 1.44 times 10 to the power minus 10, r0 is 1.2 10 to the power minus 13. I am writing it in semi because in the numerator I have the semi unit. It is 1 plus 2 to the power 1 by 3. Just do it and you will get 531.676 keV. Okay, so roughly this one. This is the so it was in semi will be cancelled out. So this is the potential, I mean Coulomb barrier. Coulomb barrier means you have to calculate the potential between two particles at a particular distance. The distance will be given, and as we are calculating the barrier, that means we have considered the deuterium and protons are at the minimum least separation. That it should not be like this. So this is the least separation, like this. There will be some distance, and that r0 value is given. Okay, so it is the 531 keV. Now going to the third problem. So gamma peak. Yeah, so the gamma peak again. We have, so remember we are considering the D plus P reaction, that means deuterium plus proton reaction. This is needed. Okay, so gamma peak for the same thing we can calculate E0 1.22 Z1 square for this Z1 square Z2 square, because deuterium has also one proton and additional one neutron. So Z1 will be Z will be 1, but the mass number will be 2, A will be 2, and mu T6 is given 15 again. So the same type problem, 15 square, and that will be 1 by third. So for this mu it will be m1 m2 by m1 plus m2. So for proton it is 1, for deuterium it is 2, and like this. Okay, so this is 0.66, 2 by 3. So 1.22 0.66 times 15 square 1 by third, that will give you 6.48 keV. So you can see the maths are very easy to do, but you have to remember this thing again. But many times I am telling this, you have to remember. So 6.48 or roughly 6.5 keV. Okay. So today's mathematics are very easy. Now coming to this part, width of the gamma peak. So till now we have calculated the E0, I mean not in the theoretical part, in the problem solving part we have calculated the E0. Now for the first time we have to calculate the delta. So delta was 0.479 Z1 square Z2 square mu T6 5 to the power 1 by 6. Let me check. Yeah, I have memorized it. Okay, so it is the same reaction, deuterium plus proton reaction. So no need to do all the other stuff. Z1 Z2 will be 1 and 1. Mu we have just calculated, which is 0.66. The same reaction we have to calculate different parameters of that reaction. It is 15 to the power 5 1 by 6. Okay, so if you do it, you will get in keV unit, that is 6.687 keV. Okay, so 6.687 this 6.7 keV. So today's problems are very easy. Now another part I will do for the theoretical thing, because you have to remember the last two questions are very good questions. Okay. Now for the maximum value of the sigma v after factoring out the S factor. Okay, so this I will do, otherwise it will be difficult. Just think 4, yeah, 5, 42.46. Yeah, so for this part we have to do some more theory. Okay, 1 2 3 4 are very easy. It was just calculation of E0 and delta. Okay, now we will go back to our base equation, that means this was our main equation with that factor inside of that, I mean outside of that integration at the first position, which I have not written in this here, that I will write. Okay, so for 5, let me start from this here. So sigma v, which was our base equation, it was 8 by pi mu 1 by kt 3 by 2 0 to infinity s e exponential minus b by e minus e by kt. Okay, this is the term. Now just focus on particular se. So this se is a function of e, energy, and our integration variable is also energy. So generally if se is a function of energy, we cannot take out the AC outside of the integration, right? Like this is like this. So suppose there is a x e to the power x dx and x e to the power x dx. These two are completely different. These two are not same integration, because the as is x is a function of the variable itself, we cannot take it out from the equation. So this is not equal to this, the same thing. So we cannot take out the s, which is a function of energy, outside of the equation. If we want to solve accurately, we have to do the whole integration. Now in this question you can see that this particular line is very important. After factoring out the s factor, that means the for simplicity, so I am writing it for simplicity, we are considering that our se is actually, just a second, yeah, is not a function of energy and it is a constant. That's why we will write it as s0. So s0 is just a constant value which doesn't depend on energy, and if this, under this assumption only, you can take the se outside of the integration. So again I am telling, it can be taken out of the integration under this assumption only, that your se is independent of energy, otherwise you cannot do it. Remember it very, well. So for this case only you can take your s0, which is a constant value, out of the integration. Okay, now so this part I have done while calculating the delta. I have shown you that this part can be written as an approximation of Gaussian term, and from that we have calculated the delta, and there was a I max term also. So let me show you, otherwise it may be confusing. This part, I was just telling that I have written the first part at I max and the second part, the Gaussian part, as like this. So this was the Gaussian approximation of the gamma peak. Okay, now if we do the same thing here, our result will be 8 by pi mu. We will just write this particular term in terms of Gaussian, 1 by kt to the power 3 by 2 and exponential minus 3 e0 by kt, which was the I max, and 0 to infinity exponential minus not e minus e0 by delta by 2, right, we write it like this, square minus, there is a minus, Gaussian de, and this s0 term is always there. So let me write it here. I am writing that s0. Oh, so the s0 term is there. Now this is the I max. Okay, and this integration, if you do it from 0 to infinity, you can find the value will be delta root over pi by 2. Okay, so all this integration can be done under the assumption of s is not a function of energy, only when this is valid. Again and again I am telling you, only when se is not a function of energy and it is a constant value, only then this is valid. Okay, so okay, now our sigma v can be written as 2 by mu, because this root pi will cancel this root pi. Okay, so that root pi will be done, and by the by putting that value here, you can find what will be the final expression. So 2 by root mu delta by kt to the power 3 by 2 s0 e to the power minus 3 e0 by kt. Okay, now this is valid only under this assumption. Now if we put our delta, which already been calculated from the Gaussian expression, the z1 z2 square mu t6 5 to the power 1 by 6, if we put that value here delta, and the e0 also, e0 1.22 or 1.2 z1 square z2 square mu t6 to the power 1/3 t6 square. Okay, just put these two value and you will get your sigma v like this 7.2 into 10 to the power minus 19. So 1 second. 7.2 10 to the power minus 19 1 by mu z1 z2 s0 tau square e to the power minus tau semicube second inverse unit. So it is a it is what I will say it, it is a type of writing. Okay, so that's 3 e0 by kt, we have been written it in terms of tau. So tau has been defined as 3 e0 by kt, where you know the e0 from this particular thing, and kt, k is also constant. If your t is given, you can calculate the tau. Okay, and here your s0 will be in keV unit. In this expression your s0 will be in keV unit, and mu, as I told you, will be in AMU unit. Just remember this. By chance you don't multiply that reduced mass with the AMU unit. Okay, so now I don't have sorry, so let me take it here. Yeah, so tau was 3 e0 by kt. Now if you put 3 by kt e0 1.2 z1 square z2 square mu t6 square 1 by 3, then you will get a value of 42.46 z1 square z2 square by t6 mu 1 by 3. So okay, you have, so this is the thing, that tau is this much only when your s is not a function of energy. Only at that time you can write your expression of sigma v like this. Okay, now that's why in this question, in question number 5, it is given that after factoring out the s factor, otherwise you cannot tell it, because you don't have given that form of s, how it is depending on the energy. Now coming to the problem, another what we have to calculate, just a second. Okay, so we have to calculate here the value of sigma v. Okay, so the value of sigma v is 7.2, this thing. Oh no, wait a second, the maximum value of the integrand. Okay, the maximum value of integrand appearing in sigma v, there is a part. So maximum value of integrand appearing in the thing is this one, not the integration, because this is the maximum value is the peak value. Okay, so that I max we have to calculate. So I max is actually exponential minus 3 0 by kt, that means exponential minus tau. This is the I max. Okay, this is the I max. Now we will calculate I max. So that is my bad, I have not written the question carefully. So it has been the maximum value of the integral, exponential minus tau, and tau we have written here, so just that thing, minus 42.46. so it is a deuterium proton reaction again. So z1 z2 is 1 for both thing, and mu is 0.66 that I have calculated, and your temperature is given 15, T6. In terms of T6 it is given 15. to the power 1 by third. Okay. So if you do this calculation, it will be 2.93 into 10 to the power minus 7. So your Imax value is 2.93 into 10 to the power minus 7. This is the answer. Okay. So I have done this little theoretical part for to give you the idea of tau, the expression of tau. Otherwise, to write it directly, it is not a good idea. So that tau is coming here into this into here. Okay, so 2.93 10 to the power minus half. So remember, try to remember that, as I told you, E0 delta. If you can remember these two, then go to that tau, which is at first, remember, it is 3E0 by kt. Then just if you can remember this E0, put it here and you will get this equation. Or if you can remember that particular equation directly, that is very good. Okay. Now, yeah. So coming to this part, the reaction cross section, the same reaction, deuterium proton reaction. All the questions are asking have been asked from the same type reaction. So here E0 is given, that gamma peak is given, T SE. Here you can see S. What in the previous problem our SE was just a constant, but here you can see SE has been given in terms of E. So here SE is a function of E. What that is A plus BE plus C square, that type of expression, it is already given. So now we can do the integration, because we know and we don't have to take anything outside of the particular integration, and we can do the full integration. Okay. So that is the thing, and we have to calculate here the cross section. Cross section means we have to calculate the sigma. Okay, and the sigma E at the beginning I have written it AC by E exponential minus B by root over E. It was from the first few slides. It's not slides, when I was deriving the theoretical background. So SE is this, and we have to calculate the sigma E. Here SE also given in terms of energy, everything is given. Your energy E0, peak of the value, is also given. Now what I will do, okay, so SE I have calculated here, and if it is this much, just a second, your E is given. Okay, right. Okay, now we will calculate our sigma at the gamma peak. Okay, so S E0 by E0 exponential minus B by E0, because that at that we have to calculate. So in place of E, we will put E0 in the expression of AC, that will give us S of E0. Now E0 is given 6.5 keV. Okay, E0 is 6 keV, that is 0.0065 MeV. It is required for our calculation, that's why I have transformed it like this. And that exponential minus B by E. Okay, so this particular thing, if you can remember it, it is good, that exponential minus B by E, what I have written at the earlier with values, it will be 30. So let me write it here. Yeah, 31.29 Z1 Z2 mu by E. If you put all the values of B in the expression, that pi, h cut, everything, then this value will be like this, and we will calculate 31.29 Z1 Z2 is 1 and 1, the same reaction, mu is 0.66, and it is given 6.5 keV, the E0, because we are calculating everything at E equals to E0, and this will be 10.023. Okay, so this part we have calculated 10.023. Now we have to, E0 is given, now we have to calculate the E0 part. So E0 part is 0.20 into 10 to the power minus 6, I am writing just this, plus 5.6 into 10 to the power minus 6 E0, because we are calculating everything at E0, into 10 to the power minus 6 E0 square. Okay, now just put E0 in terms of your MEV unit, and that means sorry 0. So this term is constant term, sorry 0.20 10 to the power minus 6 plus 5.6 10 to the power minus 6 times E0 is 0.0065 in MEV I have written, plus 3.10 in 10 to the power minus 6 0.006 0065 square, and the unit will be MEVB. Here B is actually barn, it is a unit of surface area, because we are going to calculate the sigma. Sigma has a unit of surface area because it is a collision cross section. Okay, cross section means r square, that's why this barn unit is coming. So and if we do the calculation, so S for 0.0065 MeV is actually, because E0 is 0.65 MeV, 2.365 into 10 to the power minus 7. These values I have written in my notes, that way I am putting it directly. So this is MEVB. Now we have all the equation, all the values. We will now just calculate sigma E0. So E0 is 0.00 0065 MeV. Good. That S is 2.365 10 to the power minus 7 MeV barn unit, and that 10.0.23, the exponential minus B by E0. Now this MEV will be cancelled out. So you can do it in KV also, no problem. So in that case it will be KV unit, it will be KV barn unit, okay, anything, and the result will be 1.614 into 10 to the power minus 9 barn. Okay. And if you go from barn to millibarn, it will be 1.614. Milli means 10 to the power minus 10 to the power 3, that is millibarn. From barn to millibarn. So I cannot remember the exact value of one barn in centimeter square. So and if anyone can tell, just tell me. Is it 10 to the power minus 24? I am just asking, or 10 to the power minus 22 centimeter square. I have just forgot that unit of barn. So millibarn and barn are actually unit of length square, and sigma is the cross section, that's why we have to have an unit of cross section which is coming from millibar. So this is the answer, 1.614. yes, 24 centimeter square, right? Yeah, okay. Yeah. So you can write it in centimeter square if asked in the question, but here it is in millibar. So 1.614 times 10 to the power minus 6, this is your answer. So we have calculated different things. We have calculated E0 for a particular problem, that's deuterium and proton problem. We have calculated the delta, the E0, the sigma cross section, everything we have calculated for this particular problem, and it is required at last because the last question is related to it. And we have also calculated the tau here, right, and Imax, sorry, tau, Imax, all the things for this particular reaction we have calculated. I mean, we are studying this particular reaction in great depth. So this reaction, okay. So number 6 is done. Let us go to number 7. What is the thermonuclear reaction rate? So what I have done 6, it is done 7. Yeah. So thermonuclear reaction rate, that means it is a lengthy problem, and percentage of change. Okay, this 8, 9 and 10, these are important, so important problems. Okay, so thermonuclear reaction rate, now we have to calculate the sigma V for this particular reaction. Right now we have calculated everything except the sigma V. Okay, so sigma V, from this I will not again write this equation. Let us go to this equation for the sigma V. Okay. In terms of Imax and delta pi by 2, I will write it in terms of that only. So sigma V, you can write it as 8 by pi m, sorry, c half c by kt 3 by 2. It is some just algebraic manipulation, you can do it yourself, but if you cannot do, just let me know, I will do it in the next class. Okay, so this is the your sigma V. Now for PP reaction, for P plus P reaction, some values we need to remember, that is not given, that mu, sorry, it is for DP reaction, deuterium proton reaction. So your mu is 0.67 or 0.66, we have calculated. whatever. And I max, we have calculated the I max in the previous question. Okay, that's why I was telling that all these values we need at last when we will do the last problem from that D plus P when deuterium proton reaction. That I max I have calculated in question number 5, you can see that. Okay, that S we also calculated just in the previous question. So if these values are not given, you cannot do the problem. So these values we have calculated, that's why you can treat this problem as a final problem. Okay, and we have also calculated delta for this particular problem. Everything just go through one by one the assignments, just few times before I have done it. And that E0, that peak, that everything. So this value, this value, this value and this value, these 4 values we have calculated only today from the assignment problems only. Okay, so all these values are have calculated, mu is also given. So we can calculate the sigma v by using this expression. Just we will put the delta, the I max, that SE0, everything, and the temperature is so the KT here, the temperature is not given, but I have gone through the problem, it is exactly same, that T6 is 15 Kelvin, 15 Kelvin or whatever. So what was given in the previous question, so if you use that T6, that your KT will be 1.3 keV. They should have given some temperature, but I think it is a continuation of the previous problem, that's why they have not given. So 8 by pi into m is 0.67 or 0.66. Let us put the exact value, 0.667. Okay, 932.5 MeV. Okay, half. Oh, here will be a C square. So it is nothing like the actual expression was like this: 8 by pi m to the power half 1 by kt, and the other terms we have just multiplied it by c here and c square here. That's why, that means just multiplying and dividing by c, because that's why if mc square for our case we can write it directly as 932.5 in mc square unit. That's why we have done that. Okay, and so your c is 3 into 10 to the power 10 semi per second. Sorry? You can cancel the c square, because c square to the power half is c, right? I actually cannot hear you clearly. Can you write that? Okay. Yes. Yes, exactly. So that you also can do, no problem in that, because I mean, for all the problems we have some direction to solve it in some different ways. That's why I am following that. Okay, so you can do, you cannot use that c and it will give you the same result, no problem in that. In that case you have to put the value of m only, not mc square. Okay, yeah. So 3 into 10 to the power 10 is there, and kt is 1.3 times 10 to the power keV. So keV means 10 to the power minus 3 MeV. Kilo and mega, there will be a factor of 10 to the power 3 minus 3 according to the change you are doing. And all these values of S, I max and delta, I am not writing again these values. Okay, this S, I max and delta. If you put all those values, your answer will be 19.013 times 10 to the power minus 3 barn semi second inverse, or in millibarn it is 19 into 10 to the power minus 3 barn is itself 19.013 millibarn. That is, so it is your reaction rate. So you can see the sigma should have a unit of length square, v should have a unit of centimeter per second. So this is actually the length square unit, and centimeter per second is the, so I mean by going through the dimension also or unit also we are correct. The sigma v will have this unit, length square, length, I mean length cube times by time. So 7 is done. Now going to 8. Now 8 is a good problem. Okay, so just a very simple thing. Okay, so here what I have done in the previous, here I have calculated the tau, right? Okay, and sigma v, here you can see this sigma v is proportional to tau square e to the power minus tau. I am just saying proportional to, no, not using the other value. So sigma v is proportional to tau square e to the power minus tau. You can write it. Now one thing it can be shown, I have not done explicitly, this particular thing only I have not done explicitly, so I could not get time. Using power law, it can be shown that sigma v is proportional to T to the power tau minus 2 by 3. Here T is the temperature. Okay, so if you can calculate the tau of for a particular reaction, you can find out what is the dependency of that particular reaction with temperature, because this tau is exactly this tau. Okay. So if your tau is given, the temperature, the reaction rate will be proportional to T to the power T minus 2 by 3. Remember this particular term, okay, particular expression. Now that is needed for this number 8 problem. So okay, before number 8 I will go to the number 9. It is a direct problem. So it is given the temperature dependence of Na sigma v near some energy T equals to T0 can be given by introducing a power law. Okay, that means that okay, sorry, sigma v is proportional to temperature to the power power law. It is given, and right now I just put it like this. So your power law is actually tau minus 2 by 3. If you can calculate the tau for that particular reaction, you can say the how the dependency on the P, I mean the temperature is there. Okay, so that we will do. It is a direct problem. 42.46 z1 square z2 square mu T6 1 by third. It is the same no, it is the proton reaction, not the previous deuterium proton reaction. So z1 z2 will be 1, no problem, but mu will be 0.5 and T6 is given at 15 millikelvin, million Kelvin, sorry. So 1.3 and it will be like 13.7 roughly. So you got the tau. Now your tau minus 2 by 3 is actually 3.9. So you can see, just you have calculated the tau, and from there you can tell how your temperature is, how your reaction rate is varying with the temperature. It is varying as T to the power 3.9, roughly 4. Okay, so this is important. So just try to remember this part, that write it in blue, that sigma v is proportional to T to the power p, where p is actually tau minus 2 by 3, where tau is again 3E0 by kT. All these are interrelated. E0 is coming from the gamma peak, tau is a result of the E0, and that is giving you the power law index of the temperature. Okay, and the same, so tau was 3.9 this one. Okay. Now another problem, same, but here the reaction is different. It is a alpha reaction of 12 carbon. So here also we will do the same thing, just briefly. Z1 square Z2 square mu by T6 1 by third. Now for that particular reaction, alpha, for alpha your Z1, I am considering the first particle as alpha, is 2, and for 12C your Z2 is 6, right? 12 is the mass number, that means 6 is the proton number, Z2. So that is 42.46 mu. We have to calculate m1 times m2 by m1 plus m2 in AMU unit itself. So that is, it will be, sorry, have I done any mistake? 3. So 6 it is, 6, yeah, and it is just 2 into 6 by 2 plus 6. No, pardon me, it is a long class. Okay, so mu is actually m1 m2 by m1 plus m2, not z1 z2 z1 plus z2. I was just doing that. So m1 is uh, for this m1 is 4, for this m2 is 12. So 4 into 12 by 4 plus 12, 1643, yeah, 3. And z1 z2 are 2 and 6. So 2 square times 6 square times 3 by T6 is given 200 million Kelvin by 3. That will give you a result of 54.9. Okay, so tau is 54.9. That means your power law index, power law, so that means sigma v is t to the power n or t to the power p. Let me write as p, and p is tau minus 2 by 3, right? It was tau minus 2 by 3, right? Yeah, tau minus 2 by 3. So 54.9 minus 2 by 3, and it will be 17.6. So for this particular reaction, this alpha plus 12 carbon reaction, the sigma v goes as t to the power 17.6, and the for proton reaction it was t to the power 3.9. Okay, so the power law index will depend on the elements which are taking part in the fusion reaction or any nuclear reaction. Okay, so this was, and now we will do that 8 number problem. So here it has been asked that what is the fractional change. Okay, so that means 7 8. Okay, so what is the fractional change? Now I have just written that sigma v is proportional to t to the power n or p, whatever. So let me write it, p, power law index. Now sigma v proportional to t to the power p at, okay, so it is the general form. Now suppose at temperature T1, at temperature T1, sigma v T1 is proportional to T1 to the power p, and at temperature T0, sigma v at T0 proportional to T0 to the power p. Okay, now sigma v by sigma v, okay, sigma v T1 by sigma v T0 is actually T1 by T0 to the power p. I can write it like this. Okay, now sigma v T1 minus sigma v, this is sigma v T1 and sigma v T0 at the rate of reaction at two different temperature. So sigma v T0, this is the change, and it can be written as T1. So okay, so let me write it like this. So it is actually sigma v T1 by sigma v T0 minus 1, right? I mean this expression I have not this sign I have removed. Okay, so sigma v T1 minus sigma v T0 by sigma v T0 can be written like this, right? And this particular, the first term has been given by this T1 by T0 to the power p. Just I will replace T1 by T0 to the power p minus 1, right? It can be written like this. Now we will have to calculate the rate percentage change. So this is the change of reaction rate. So this is the numerator is actually delta sigma v, that is the change between sigma v T1 minus sigma v T0, that is delta sigma v, which is the change, divided by the initial sigma v, which tells you the fraction of change. Now we will convert it into the percentage change. Just we will multiply it with the 100. So T1 minus sigma v T0 by sigma v T0 times 100, that will give you T1 by T0 to the power p minus 1 times of 100. Okay. Oh yes. Now okay, so okay, so now this we have to calculate. So p is equals to tau minus 2 by 3, which has been shown, and tau is 42.46 z1 square z2 square mu by T6 to the power 1 by 3rd. Okay, and it is again the deuterium proton reaction. that D plus P reaction. For that we know the mu value 0.667. All the values we have already calculated, I will not again tell. So if you just put those values, your tau will be 15.043. okay, just put the Z1 Z2 mu for this particular reaction, which I have calculated already. So 15.043, that means your P will be 15.043 minus 2 by 3, that will be so 4.348. this is your P, this factor. So I will just put here T1 and T0. So we have to use the what is the value of T1 and T0. So we have to calculate the percentage in the reaction rate at a stellar temperature T to the power T equals to 20 million Kelvin, and you can see that it is there is the initial temperature is not given, but as I told you, it is a continuous problem of deuterium plus proton reaction. We will take the T0 as 15 millikelvin, which is given in the earlier question. So we have to calculate the change of reaction rate from 15 millikelvin to 20 millikelvin. Okay. So T1 is or 14 million. Sorry, I am telling milli. It is a bad mistake. It is million, not milli. 15 million Kelvin to the power P. P is 4.348 minus 1 times 100. This is a percentage, and if you calculate, it will be 249.7%. So you can see that reaction rate has been changed from 15 million Kelvin to 20 million Kelvin by a factor of almost 250%. That is the answer needed for the required for this particular question. So this is the fractional change. Now okay, so if you have any question till now, so it was the main problems which I want to discuss in this particular session. But one thing I lagging behind, that is the nuclear cell model and the liquid dwarf model. So there are one or two questions from that new cell model and the liquid dwarf model. I thought that I will cover it today, but it is not possible. Because it is already 2 hours almost. So I will go to that. I will go through that liquid dwarf and cell model very briefly in the next session. At first, at the beginning of the class, I will just go through that two model and I will solve the question which is given in the assignment, that I will do in the next class. So and another problem is there, I think this problem. So mean lifetime of combustion of 2 protons into deuterium in the sun. So this type of problem, the same type problem I have done in the last day, but there all the values of sigma v, mean value of sigma v, everything was given, because till the 3rd week you do not have the idea of S factor or anything. But the same question has been asked in the assignment in such a way that for this question nothing is given. You have to calculate the sigma v, mean sigma v, everything from the knowledge you gathered in the 4th week. So that sigma v here you have to calculate, but in the previous problem it was given. So in the last class I have just used that value and I have calculated. That was very easy, but now I want to calculate it. So I will just go through it within 7 to 8 minutes and we will end the class. Okay, no problem. So okay, so mean lifetime, we have to calculate the lifetime, and in the last week I have shown you that the lifetime is actually n sigma v. N is the number density. Now 2 protons into deuterium, so number density of protons, proton plus proton deuterium. Now so we have to calculate the sigma v, which is not given in this particular case. So sigma v is exactly the same thing. Let me go to it. Yeah, this one, sigma v 7.29. Just a second. Yeah, this one we will use. Sigma v 7.2 into 10 to the power minus 19 with the other factors. We will use this particular expression. Okay, sigma v, so 7.20 10 to the power minus 19 1 by mu z1 z2 tau square exponential minus tau s of e0 semi cube second inverse. Okay, so for proton z1 z2 is equals to 1. T as in the sun, so in the sun the T is actually 15 million Kelvin. We will take the T6 as 15. Okay, so T6 we will take as 15 and mu is 0.5 for proton. So first we will calculate the tau, that is 42.46. in the last class, if I have written this type of expression, we could not have understood it, so that's why I did not do it in the last class and I will do it today. So 13.665. now it is very familiar to you, no problem of understanding it. So tau is 13.665 and s of e0, this you can calculate in the same way. I will not calculate. It is 3.8 into 10 to the power minus 22 kVb, exactly similar way which I have done, but it is given in a particular book. So it is page 335. The book is, the name of the book is CA Cauldrons. I should write it in a good way. CAULD. I think you have the book. In the cosmos.
Sir, I am not getting this book in the internet.
Okay, I also don't have the access right now. I will try to find it, and if I can get, I will put the DIV link in the chat box in the next session. Okay, I will try to find it. Yeah, it is important because this expression, otherwise if it is not given anything in the question, you cannot calculate. Okay, because as you can see in the previous question, when we calculate the SE0, so here just a second, here SE0, the expression was given, that's why we have calculated the SE, but here the expression, how the function looks like for SE, it is not given. I don't know exactly whether they are using the same expression as the previous questions or not, so that I don't actually have gone through. I will just try to I verify it also, that if that same expression is giving me this value, so this value is important. But if this problem is given in your exam, the dependency of SE on energy will be given. You don't have to remember anything. Okay, and if you use these values, then your sigma v will be, just put this SE0 tau square, which I have calculated, and mu z1 z2, you will get sigma v as 1.187 into 10 to the power minus 22 centimeters cube second inverse. Okay. And another thing which is required, that is also covered in the last week's lecture, that is NH, the number density, can be written as like this. I will not go into details because you already know it. And if we put that rho, you should have been given. So I don't know from where they are using all these values. That's why I don't think this problem is very good, because all the values are not given. So rho is given as 100 gram per semi cube. If it is not given, it is not possible for a student to solve this problem. Na is okay, 0.6.023 10 to the power 23 mole inverse, and mu x is 0.5. So all these values should be given. Okay, so 0.45 I have taken for x age. That's why I put this problem at last, because it is not a good way to state the problem. Rho is 100. If you use all these things, 1.007825 gram mole inverse, then you will find NH as 2.986. Just follow the procedure. I mean, if you have given some problem like this, what you should have done, that first calculate the tau. Your S function of S will be given. From that, just calculate the SE, and your NH, everything, rho, x age, everything will be given in your proper exam question. So everything will be given. Just calculate these three things: the tau first, then S, and then this NH. Okay, so just follow the procedure, not the values. These values are not important. So if you have all this, so mean lifetime can be calculated by 1 by NP sigma v. So just put your NH, which we have calculated, NH or NP, whatever, hydrogen and proton is same, we don't consider the electron mass, and sigma v you have already calculated, just put it here, you will get the answer for this particular problem, which is 8.94 10 to the power 9 years, but it is the general procedure of solving that. That mean lifetime depends on the mean sigma v and the NH. So sigma v, for sigma v you need S and tau, just calculate the tau and S from that sigma v, and then NH from this particular equation. Okay, so this is the method. So what will be the answer? It is roughly 9 times 10 to the power 9 years, 9 giga years. So I think it is given 9 times 10 to the power 9 giga, it is the answer. So this was the problem, but all the data are missing. I don't know from where they have taken those values of rho, xh or everything. So this is the class, and the last question is astrophysical S factor is more useful than cross section, because it is directly asked from the class that when as a more useful than the cross section, because it varies smoothly with beam energy for non resonant reaction, because we have seen in the class itself that S factor is useful only when we consider the non resonance reaction. For resonance reaction we have to deal it with the separate method. Okay, so these are the main questions. So next day at first I will go through that cell model and the liquid drop model. Okay, so that is I have to cover, which is from the earlier classes. So that I will cover, and all the new materials which will be available in the 5th week, that I will cover. So for today I am done with the class, and if you have any question or any inquiry, you can ask. And I don't Sam Chintanpalli, you told me that you will send me the assignments, just do it. Okay, and if you have any questions you can ask, otherwise we will end the class here today.
Please provide that book in the next class.
Yeah, I will try to do it. Yeah, sure. Okay.
Thank you.
Yeah. Okay, then bye, and I am ending the session today. Okay. Thank you.